All right, good afternoon. Just picking up sort of where we left off yesterday, and we started to go into radical equations, and we will get back to those. First of all, let me look over once again equations involving radical expressions and also quadratics, and we have from page 69, okay, and we have in number 82 we're looking at solving for the variable z, okay, whereupon we have 7 plus 20 over z is equal to 3 over z squared. And now, again, we have in this presented equation, okay, z is located in the denominator position, and I'm trying to put z in direct terms. Now, in terms of whatever we have for z, okay, if you notice, we have z placed as denominators of these two fractions, and the restricted value of z is going to be at 0. First of all, okay, we have our 20 over z. Again, for a fraction to be defined in the real number system, z cannot be 0, and we have that z squared cannot be 0, okay, and there's only one number that will square to 0, and that is going to be 0 itself. Okay, so we have altogether, okay, we have just with the long restriction regarding z. Again, we have that z cannot be 0 in value, okay. And in terms of being able to work with our fractions, okay, again, we have just pulling, okay, what we have in the case of the least common denominator. Okay, so you have z and z squared. And again, the smallest term that both z and z squared will go into is going to be the higher order that we have in z, which is going to be z squared. Okay. And so if we multiply all terms out by z squared so as to clear the fractions, okay, so we'll have 7 times z squared. And we have plus 20 over z, okay, to be multiplied by z squared. Again, clearing out the fractions. Okay, we have 3 over z squared times z squared. So for what we have in the formation case, we have 7z squared, and for what we have in the makeup, so it's 20 over z. So we have 20 times z squared, so we have 20z squared over z. And we have is equal to 3z squared over z squared. And if you see the cross multiplication simplifying in advance, that is fine. Okay, so we have for the first term, we got 7z squared. We've got plus 20 z squared over z. Z squared divided by z leaves us with z. Okay, so you have 20z. And then we have to the right, we got 3z squared over z squared, so this will leave us with 3. Now we got a quadratic equation in the variable z. And right now, okay, if I put this in standard form, I'm looking at setting the equation to 0. So, in looking at moving the 3 over, okay, so I have 7z squared plus 20z minus 3 is equal to 0. Okay. And okay, so we have a quadratic equation in standard form, and there are various approaches you can take in order to arrive at the solution. And you could try the quadratic formula, though you would be dealing with some potentially unusual coefficients. And you can also utilize the zero product property. And for what we have in the setup, so again, we started out with this equation and we cleared out the fractions upon multiplying everything out by z squared, where I came out to this set of terms, and now I have the items arranged such that we have the equation in its standard form. Now, again, there are ways that you can follow through. Now, this trinomial is factorable. So you have where 7z squared plus 20z minus 3. And if you were to factor, again, factoring by grouping is a pathway forward. And looking at what we have here, okay, so we have with the first and the last coefficients, okay, we have 7 and negative 3. So we have 7 times negative 3 comes out to negative 21. And once again, involving the coefficient 20, again, so we're looking for factors of negative 21 that will add up to 20. Now we first started out, okay, to getting to negative 21 upon multiplying 7 and negative 3. Again, 7 times negative 3 is negative 21. 7 plus negative 3 comes out to 4. Okay, but we need the right combination where the sum is at 20. And so we'll have more weight given to the addition than to the subtraction side. And just to put the terms in order, okay, so for negative 21, okay, negative 1 and 21 will be the combination. Negative 1 times 21 is negative 21, and negative 1 plus 21 comes out to 20. And looking at what we have in this trinomial and setting the stage for factoring by grouping. With the negative 1 and the 21, they'll be used to form z terms upon splitting 20z. Now technically you could have the coefficients in either order, but I'd rather have the positive term or coefficient to follow the negative, and that is to ensure that the middle operation separating the groups will be addition, so I don't have to worry about factoring out any negatives. Now, for what we have in this sequence of terms, so we have 7z squared minus z and we have plus 21z minus 3. And entering the stage of grouping. So we have 7z squared minus z. And we have in the middle is going to be the operation of addition. And grouping together the last two terms, I have 21z minus 3. Okay. Let me mention, if I had it plus 21z minus z, you could do it that way too, but your middle operation would be subtraction, and I had to envision the last two terms being where in factored form you would be in the mix factoring out negative 1, but with a plus in the middle I do not have that added burden. So looking at what we have now with 7z squared and negative z, okay, we have a common factor with the variable z, and taking 7z squared minus z and dividing by z, so we come out to 7z minus 1, and bringing down the plus factor, highest term that will go into both 21z and negative 3. Okay, that is going to be at 3. And 3 into 21z minus 3. Okay, this would be 7z minus 1. And looking at what we have now, okay, between the groups we have a common binomial factor with 7z minus 1. And for the other factor, okay, this will come from grouping together the greatest common factors and uniting operation with addition. So we have z plus 3. And you can always go back and check. 7z times z becomes 7z squared. Then we have 7z times 3 is 21z. Inside product is going to be negative 1 times z, which is negative z. So we got 21z minus z becomes 20z. And negative 1 times 3 is negative 3. And so going back to what we have in the original equation. Okay, so we have this trinomial factored and taking 7z minus 1 and z plus 3 into the equation. Okay, so we have the backdrop whereupon we can perform factoring. We're going from factoring to utilizing the zero product property. Okay, so we have for this equation, okay, so these are our factors and utilizing the zero product property. Okay, so I can set each of the factors to 0. So one potential solution is going to stem from taking 7z minus 1 and setting to 0. So we have 7 times z is equal to 1, and we have with division by 7, we're going to have one apparent solution at 1/7. As for z plus 3 is equal to 0. Okay, so we're going to have, taking away 3 from both sides, we're going to have that z is equal to negative 3. And for what we have in terms of any potential constraints, again, this was the equation we started out with. And the restriction was that z cannot be 0. So looking at our values, we have 1/7, which is non-zero. Negative 3 is also non-zero. So this equation is going to have two solutions in the variable z. And those results we have with positive 1/7 and negative 3. Now, in the case picking up, okay, where we had with radical equations, and let me mention something about radical equations. The examples we looked at had the variable to appear one time. And let me give you a case where you might have the multiple appearance of the variable in the equation. Now let's say we have a case here where we are looking at solving for x. And we can have in the equation, okay, let's say we have x is equal to the square root of 4x plus 12. Okay, so I have x is equal to the square root of 4x plus 12. Okay, now, okay, we have x by itself on the left. We also have x to appear in the binomial 4x plus 12, whereupon we are taking its square root. Okay, and what I can do is that I can remove the square root by taking both sides and squaring out. And upon doing so, okay, so I have x squared is situated on the left, and to the right, okay, we have the square roots. Again, if you had an index number explicitly given, that would be with the index 2. So the exponent, if it matches the index number of the radical, you're going to have cancellation or complete removal of the radical. And so this will free up the inside expression. So we have that x squared is equal to 4x plus 12. Now we have in this situation, okay, we have a quadratic equation that we can convert into standard form. So again, we have x squared is equal to 4x plus 12. And if I set this up where we have equal to 0, and we can accomplish this by taking the terms from the right and deducting on both sides. So we're going to have here in the setup, we got x squared minus 4x minus 12 is equal to 0. And here we have a trinomial, okay, that is factorable. So we have an x squared, okay, so this will go to x and x. And factors of negative 12 whose sum or difference will be at negative 4. Okay, this signals that more weight will be given to the subtraction than to the addition. Okay, so we have x plus 2 and x minus 6. Again, 2 times negative 6 is negative 12. 2 and negative 6 add together to form negative 4. Now, we're going to have two apparent solutions. If I set x plus 2 equal to 0, we're going to have that x is equal to negative 2. And if we have x minus 6 equal to 0, okay, we're going to have that x is equal to 6. Now we're going to be checking the result. And so we might have two solutions, or we might have just one solution. And we also might have possibly that neither solution is going to work out. And what I'm going to do here, at least in this example, I'm going to check what we have for these values. So if I were to check x equal to negative 2, okay, so this is the equation we have, and we're looking at whether negative 2 is going to fit into this equation. So we have x at negative 2 and for 4x plus 12, so I have 4 times negative 2 plus 12 and 4 times negative 2 is negative 8. Yeah, plus 12. Negative 8 plus 12 is 4. Okay, now, again, we had the square root of 4. And again, with the principal square root rule, okay, this states that the square root or any other even root of an expression cannot reduce to a negative constant. So there's going to be only one value that is going to be the square root of 4, and it's not negative 2. Instead, it will be positive 2. Okay. So in this case, trying to work out x equal to negative 2, that's trying to say that negative and positive 2 are equal, and this is going to be a false statement. So -2 does not check out. So now we're going to have at most potentially one solution, and this is going to be with 6. Okay. Okay, so if I check x equal to 6, okay, so going back to our equation. Okay, so this time replacing x with 6. Okay, so yeah, 6 is equal to, now for the square root of 4 times 6 plus 12. Now 4 times 6 is 24. And add it to 12. So we're going to have the square root of 36. And the square root of 36, again, now two numbers were square root of 36, but for the square root of 36, we're looking at just the positive value, and that is going to be a 6. And 6 is equal to 6, so that is true. So the tested value for x set to 6 will ring true. And so this particular equation will have one solution, and that is going to be with 6. Right. Now, in the case of what we have with the radical equations, and we have on page 70, and we have looking at solving and we have with number 103. Okay, so okay, now this one starts out with solving for x. Okay, so you have 1 is equal to -2. And we have plus the square root of 2x plus 7. Okay, so x appears once, and it's inside the radical within the expression 2x plus 7. And what I can do to get the square root of 2x plus 7 by itself is to undo the presence of -2 on the right. So I can take -2 and get this to go out upon adding 2 to both sides. Okay, so I have 1 plus 2. Okay, this will make 3. And we have that 3 is equal to the square root of 2x plus 7. And you can leave these terms as they are at this stage, but what I'm going to do, I'm just going to switch around, kind of like go from b is equal to a is equal to b format, and just have the radical on the left. So to ensure that the x term is on the right, it's just, or to say have x term or expression on the left. This is just a preference, but if you kept this where it is, that's fine. And so we're going to remove the radical upon squaring both sides. And so we're going to have the square root of 2x plus 7 squared. So this will be 2x plus 7. And 3 squared is 9. And getting the x term by itself. So if I take 7 away from both sides, now we're going to have that 2x is equal to 2. And we have with division by 2. Okay, we're going to have that x is equal to 1. And let me just mention, okay, so you have in this one you can check your result. Okay, So you got 1 by itself on the left, and I want the right hand side of the equation to also be at 1. Okay, so we have with x at 1. Okay, now 2 times 1 is 2. 2 plus 7 is 9. Now the square root of 9 is going to be at 3. Negative 2 plus 3 is going to be 1, and 1 is equal to 1. Alright, so this is a case of a radical equation that has x to appear once. Now, and what we have now for, say if we look at 104, now we have also in the variable x, okay, so we had that 6 is equal to 9 plus the square root of 5 minus 3x. Okay, so we have the setup in 104 like 103. So you have constant by itself on the left, and we have radical term following the constants on the right hand side. And just setting things up here, if I get the radical by itself, okay, so I can take 9 away from both sides. And here we have 6 minus 9 is equal to negative 3. And we have negative 3 is equal to the square root of 5 minus 3x. And if I just do the commutative property switch around, like b is equal to a is equal to b, okay, and if you notice we have an even root radical expression, and again with the principal square root rule, okay, the principal square root rule again states that the even roots of an expression cannot reduce to a constant that is negative. Guess what? Before had the even root of an expression equal to positive 3. Now we got the even root of an expression trying to reduce that to negative 3. And it's because of the negative here that we don't even have to continue to try to solve for x, because automatically by the principal square root rule there is no solution. Again, no solution, and the reason being the principal square root rule. Now, in the case of what we have with 105, okay, so transitioning over to working with the letter x, to trying to solve for the letter m. And in this case, you have the square root of m plus 18, followed by the addition of 2 is equal to m. Okay, so m appears twice. Okay, so we have a situation kind of similar to what we have here, where we had x to appear twice. Now, in m, okay, so I have the square root of m plus 18, followed by the addition of 2 is equal to m. And if I look at isolating the radical term or expression, which can be done upon moving the 2. So if I look at subtracting 2 on both sides, so I have the square root of m plus 18 is equal to m minus 2. And to remove the radical, again, so we have a square root. Square roots can be done by squaring. So in this case, if we square both sides, Okay, so the left-hand side becomes m plus 18. And just a reminder, okay, in the case the square of m minus 2 okay, so you have m minus 2 times itself. Okay, so you have m times m becomes m squared. You got minus 2m minus 2m. Negative 2 times negative 2 is 4. And combining the outside and inside product, so we have m squared minus 4m plus 4. So we got a quadratic equation. Okay, so we have with the highest order term in m at m squared I can set the equation to 0. And what I can do here with m squared right now at the right, I can just move the terms from the left. So we have upon subtracting both m and 18, so we're going to have that 0 is equal to m squared minus 5m minus 14. And to set things up, okay, I'm going to do a switch around. Again, this is optional. But with m squared minus 5m minus 14 equal to 0, okay, I have the created pathway to utilize the zero product property. Okay. So upon factoring m squared, okay, this will go to m, and factors of negative 14, whose sum or difference will be at negative 5. So we have m plus 2 and m minus 7. And for the m plus 2 factor, we'll have an apparent solution with negative 2. And setting equal to 0, the binomial m minus 7, we have potentially that m is equal to 7. And just looking at checking what we have now. Okay, so if I check out negative 2, again, you don't have to write this out. You can sort of do like a bit of a visual check. But with m at negative 2, so yeah, the square root of negative 2 plus 18 plus 2 is equal to m, which we have right now at negative 2. Now negative 2 plus 18 becomes 16. So we got the square root of 16 plus 2 is equal to negative 2. Now, again, for the square root of expressions, they cannot reduce to negative constants. So for the square root of 16, this is 4 and only 4. And for what we have in the follow through, okay, we have the left hand side becomes 6, while the right hand side is m, which we had entered as negative 2. So this part is false. So the attempted solution at m is equal to negative 2, okay, that is not going to check out. Now, for the other possibility. Okay, so we have with m equal to 7. So we have, filling in, so you have the square root, and we have a 7 plus 18 plus 2 is equal to 7. 7 plus 18 is 25. And the square root of 25 is going to be at 5. And we've got 5 plus 2. Right hand side is at 7. 5 plus 2 is 7. And 7 is equal to 7. So that is true. So it turns out that 7 will check out. So this equation is going to have one solution, and that is for m is equal to 7. All right. Now, again, we have a mix of even root radicals as well as odd root radicals. And now, just in the case of another scenario, kind of like what we have in the variable m, now we have in problem 106. Okay, and in this one case, so we have the square root of 2n plus 29 followed by the addition of 3, okay, is equal to n So you have a little bit of history to repeat. Okay, so you have variable expression, then you have inside the radical, and then you have the letter we're trying to solve for by itself on the right. So you have that bit of history. To show up once again. Okay, so if I look at isolating the radical, in this case, subtracting 3 on both sides, so I have the square root of 2n plus 29 is equal to n minus 3. And looking at squaring both sides, so you got the square root of 2n plus 29 squared, so this will be 2n plus 29. Again, for the square of n minus 3. We have n minus 3 times itself. So we have n squared minus 3n. Inside we have also minus 3n. Last product is going to be a plus 9. So we have n squared minus 6n plus 9. So we have another quadratic equation. Okay, now the highest degree term, okay, we have it n to the second. And once again, we have from the left, okay, I can move these terms over, moving 2n by subtracting, as well as 29 also by subtracting. So we're going to have 0, to which we're going to have set equal to n squared minus 6n minus 2n, which will be negative 8n, and 9 minus 29, okay, becomes negative 20. and just re-expressing with the variable terms on the left and 0 on the right. Okay, I have a factorable trinomial expression. So we have an n squared going to n times n. Then we have factors of -20 whose sum or difference will be -8. And upon setting each of the factors to 0, okay, so we have n equal to -2, and for n minus 10 is equal to 0, we'll have that n is equal to 10. Okay, so we got two apparent solutions, but to see how these values will work in the original equation, okay, so for what we have in this case, right, so for -2, okay, so the right hand side you'll have it -2, and on the left you have 2 times -2 is -4. -4 plus 29 is 25. Now again, the square root of 25 is 5. It's got 5 plus 3 is 8. And trying to have that to agree with the right hand side with n at -2, and 8 and -2 are not the same. So in the case of -2, this is not going to check out. We have with 10, see if this works. Okay, so n is at 10, and you want the left hand side to also amount to 10. So we got 2 times 10 is 20 plus 29 will make 49, and the square root of 49 is going to be at 7, and 7 plus 3 is 10. Left hand side of the equation is 10, and right hand side of the equation is also at 10, and so 10 is going to check out for this equation. And in general, okay, for equations that have even root radicals, such as square roots, it is recommended that you check, but if you have odd root radicals and you got the setup and the follow-through correctly done with the algebra, because you don't have the burden of the principal square root rule to deal with odd roots, the burden of checking and rechecking is not so mandatory. And we have, in the case of odd root radicals, now we have, in the case of 107, and here we have -4, we have times the cubic root 2x minus 5, okay, followed by the addition of 6, and we have that equal to 10. Okay, so we get the radical term by itself. And so for what we have here, okay, so I can undo the presence of the addition of 6. So I can subtract this. Now we have -4 times the cubic root 2x minus 5 is equal to 4, and I can divide by -4. So you have with the cancellation, -4 over -4 goes out, so we have left standing, we've got the cubic root of 2x minus 5 is equal to, and 4 divided by -4, positive over negative is going to be a negative. In this case we have -1. And let me mention, okay, so had this statement been the square root of 2x minus 5 or any even root of 2x minus 5, and I tried to set this equal to -1, there would be no solution on the basis of the principal square root rule. But again, this rule does not apply to odd root radicals, so I can follow through on this one. So to undo the presence of the cubic root, I can take both sides and raise to the power that matches the index radical number. So that's going to be 3. So taking both sides and raising to the third power. So left hand side, okay, so we have 2x minus 5. And -1 times itself times itself. This is going to stay at -1. So here I have a two-step linear equation. And isolating the 2x. So if I add 5 to both ends, okay, we're going to have 2x is equal to -1 plus 5, which would be 4, and a 2 times x is equal to 4. Okay, we're going to have the x is equal to 2. And with this being an odd root radical, again, the double checking is not so mandatory as it would be for even root radical expressions. Now, in the case of what we have with 108, okay, so going from a cubic root to a fifth root. And here we have -3 times the fifth root of 4x minus 1. We have plus 2 is equal to 8. And just taking what we have now. Okay, so if I isolate the radical, just like I did over here, I can undo the presence of addition. In this case, so I'm taking out this time 2. So I now have -3 times the fifth root of 4x minus 1 is equal to, and 8 minus 2 is going to be at 6. And now dividing by -3, so as to free up the fifth root of 4x minus 1. Alright, so I have the fifth root of 4x minus 1. We have is equal to now 6 over -3. Okay, so this is going to be a -2. And to free up 4x minus 1. Okay, so I'm undoing the radical by now taking both sides and raising to the fifth power. So what I have on the left, okay, so I have 4x minus 1. And for -2 to the fifth, okay, so you have like, you got -2, okay, to the second is going to be 4, to the third is -8, to the fourth you have 16, and then to the fifth you have like 16 times -2, so we have -32. And getting the x by itself, we have upon adding 1, okay, so we're going to have that 4x is equal to -31, and we have with division by 4, you can express either as a fraction, and since like a calculator result, since the decimal is going to end at the second place. We can also write this as negative 7.75. And there are some other special cases with radical equations, and we will get back to these. Okay, but for right now, okay, there is another type of equation, and this is going to involve absolute value. And in the case of absolute value equations, and it's likely that most of you have dealt with absolute value in some way, shape, or form, and it just basically involves the distance away from zero. Okay. And just for the algebraic notation, for the absolute value of x, okay, this can be written as what will look like x inside vertical bars. And by definition, okay, so you have the absolute value of x okay, this is going to be the number of integral steps that x is going to be away from zero on a number line. Okay, and we have just regarding absolute value. Okay, absolute value is going to be a non-negative quantity. And just for absolute value, okay, say if you have like inside the bars, okay, so if you have like that, if you have like in bars like 14, this is referring to the absolute value of 14, and 14 is going to be 14 steps away from zero. So the absolute value of 14 is equal to 14. And even for the absolute value of a negative, think of like negative 37, this will be like in its own capacity, 37 steps away from zero. So that's going to be 37. Now for the absolute value of zero, no distance away from zero, so that is equal to zero. So absolute value of a positive is a positive, and when you have a negative value, even its absolute value is going to be positive. Okay, so these are just samples of the determination of absolute value. Now where the equations come in regarding absolute value, okay, there is a rule. Say that if we have that k is a non-negative value, okay, non-negative value. What I mean by this is that k is greater than or equal to 0. And we have that the absolute value of x is equal to k, then what x is going to be equal to is going to be positive or negative k. And to kind of give you some visuals where the equations are concerned. Okay, say if you're looking at solving for x, and we'll say that we have here that the absolute value of x is equal to 7. Okay, so this is a case where you have directly absolute value of x is represented by itself. Now k is going to be 7, and 7 is non-negative. So what could x be? Well, we have that the absolute value of x is equal to 7. So in terms of what x is going to be, it'll be that value or a set of values that will be 7 units away from 0. Okay, so we're going to have 7 and also possibly negative 7. So there are two results for x. And those numbers we have a negative and positive 7. So you have like the absolute value of negative 7 is equal to 7. And the absolute value of 7 again is equal to 7. So we have two solutions for x in this case. And let's say that if we have sort of a multi-step equation. Now if I have the absolute value of 2x minus 7 plus 2 is equal to 19. Okay, and I'm looking at solving for x. Okay, so I have x to appear once, and that is with the absolute value term where I have the absolute value of 2x minus 7. Okay. And what I want to do here is to get the absolute value term by itself. So I can just take 2 away from both sides. So we have the absolute value of 2x minus 7 is equal to 17. Okay, so let me pause right here. Okay, so here I have an absolute value term. Now, corresponding to what we have theoretically. Now, the absolute value of x is represented by the absolute value of 2x minus 7. And we have now the k value is going to be 17. And removing the absolute value bars, going from 2x minus 7 to just 2x minus 7. And this binomial will be set equal to those numbers that are 17 units away from 0. And those will be positive and negative, 17. So looking at solving for x, what does this mean here? It means we're going to branch out into two equations. One where we have at the lower ends, we have 2x minus 7 is equal to negative 17. And we have at the other ends, we have also possibly that 2x minus 7 is equal to 17. All right, so looking at what we have in x. Okay, so I can add 7 to get the 2x by itself. So we have that 2x is equal to negative 10, and if 2 times x is negative 10, then we're going to have that x will be negative 10 divided by 2, and so we're going to have that x is equal to negative 5. Now if I have that 2x minus 7 is equal to positive 17, okay, I'm still going to isolate the 2x upon adding 7 to both sides, and so I'm going to have that 2x is equal to 17 plus 7, which will be 24, and x would be 24 divided by 2, so x is equal to 12. Okay. And so we're going to have two values that will fit for x in this equation. So we have a negative 5 and positive 12. Okay. And in a sense, you could go back and check. Okay, say if we have with 12, you got 2 times 12 is 24 minus 7. 24 minus 7 is 17. Absolute value of 17 is 17, and 17 plus 2 is 19, which is equal to 19. And we have a negative 5. 2 times negative 5 is negative 10. Negative 10 minus 7 is negative 17. Now, the absolute value of negative 17 is going to be 17. 17 plus 2 is 19, equals 19. So both of these values will check out. Now, third case. Okay, this is going to be short, but it's just going to emphasize a point. If we have, let's say, the absolute value of x plus 5 is equal to negative 16. Okay, so we have the absolute value term in the form of the absolute value of x plus 5 is equal to negative 16. Alright, so you have the absolute value term by itself, and if there is to be a solution, okay, k has to be at the right setting, and let me stress, so that which had to be k, looks like we have represented by negative 16, but here we have that k is supposed to be a non-negative value. And guess what? Because we have a negative sign here, we had the violation of any potential solution for x. Okay, so you had that the absolute value set to be negative, well, automatically, because of the negative sign here, there is going to be no solution. Now, another case involving absolute value equations, and this will be consisting of sort of a multi-step operation, and this example is going to serve additional purposes along with just solving for x, and this is how to go about treating the grouping symbols, namely the absolute value bars. And let's say if you have like negative 3 times the absolute value of 2x plus 6 followed by the addition of 6 is equal to negative 24. Now for this particular setting, let me mention, there can be the temptation to try to distribute negative 3 over 2x plus 6. So let me just go ahead and mention. Okay. Okay, do not treat like the absolute value of 2x plus 6 as if you had 2x plus 6 in the parentheses. Okay, so what is going to be the pathway forward to solving for x in this case? Well, if you notice in the prior examples, okay, we had the backdrop to where we had the absolute value term to be isolated. And we're going to do the same thing here. Alright, so we get the absolute value of 2x plus 6 by itself. First of all, we can undo the addition of 6 by taking this value away from both sides. And so we'll have negative 3 times the absolute value of 2x plus 6 is equal to, now we got negative 24 minus 6, so this will come out to negative 30. Now, in the case of the negative 3 in front, we're going to take care of the multiplication here by dividing. Now for what we have here, okay, so dividing both sides by negative 3. So we're going to have the absolute value of 2x plus 6 is equal to negative 30 over negative 3. Negative over negative is going to be a positive. So that is going to be equal to 10. So you got your absolute value of x represented by the absolute value of 2x plus 6. And your k value is 10. So this is non-negative. So for the values of x we're going to have will be such that whatever we get for 2x plus 6, the absolute value is going to be at 10. And those numbers with an absolute value of 10, we have at positive and negative 10. And just setting up what we have for x. Okay, so you have simultaneous equations. So we have 2x plus 6 is equal to negative 10. And we have that 2x plus 6 is equal to 10. And looking at solving for x, okay, so if I get 6 deducted from both sides here for 2x plus 6 equal to negative 10, so I'm going to have that 2x is equal to negative 16, and we have at one end, okay, we'll have the x is equal to negative 8. And for what I have in the case of 2x plus 6 equal to 10, if I take 6 away from both sides, so I have 2x, 10 minus 6 is 4, and if 2 times x is 4, where we're going to have that x is equal to 2. Okay, and so for this equation, okay, there'll be two results here for x. One at negative 8 and the other at positive 2. Okay, now for what we have concerning absolute value equations, and I'll tell you what, just for what we have here, and there is something about radicals that I'm going to want to go ahead and discuss. And in the case of absolute value equations, let's see what we get for the absolute value of x is equal to 15. And also for the absolute value, and we'll say we have of 2x, absolute value of 2x is equal to 22. And also, let's see what we get in the case of let's say we have negative 4 times the absolute value of 2x minus 2 plus 10 is equal to negative 54. So the first two, okay, fairly short answer, but the third one, okay, that one might require quite a few steps. So for the next few moments, let's see what we get for x in these three problems. Two numbers with an absolute value of 15, so going from the absolute value of x to x. So we have x is equal to plus or minus 15. And so we have in the solution set, so we're going to have the x is equal to negative 15 at the lower end and 15 at the upper. Again, absolute value of negative 15 is equal to 15, and the absolute value of 15 is 15 once again. Now, for what we have in the case of the second item, and we got the absolute value of 2x is equal to 22. Okay, so you have the absolute value of x represented by the absolute value of 2x, and k is represented by 22. So if I remove 2x from the absolute value notation, so we had that 2x is equal to the numbers that will be 22 units away from 0, and those are going to be positive and negative 22. Okay, so we're going to have a couple of possible values for x. Going to be whereupon we have 2x is equal to negative 22, and also where we have 2x is equal to 22. And if we have that 2x is equal to negative 22, okay, so we have the x is equal to negative 11, and if 2 times x is equal to 22, where we're going to have the x is equal to positive 11. Okay, so you got like 2 times negative 11 is negative 22, and the absolute value of negative 22 is positive 22. For 11, about 2 times 11 is 22. Its absolute value, likewise, is 22. Now, in this third case, in looking at solving for x, okay, now we have negative 4 times the absolute value of 2x minus 2, followed by the addition of 10 is equal to negative 54. And if I isolate the absolute value term, so again, I'm not going to treat this part as you would 2x minus 2 in the parentheses. We're going to isolate the absolute value of 2x minus 2. So we're going to manipulate moving the negative 4 as well as the 10. And I can proceed by undoing the addition of 10 by taking 10 away from both sides. So we have negative 4 times the absolute value of 2x minus 2 is equal to negative 54 minus 10. So this will be negative 64. And to take care of the negative 4, okay, we'll have with division. So in dividing by negative 4, okay, so this is going to come down to the absolute value of 2x minus 2. Okay, so 2x minus 2, still the absolute value notation, and negative 64 divided by negative 4 is going to be a positive 16. And upon removing the absolute value bars, okay, so we're going to set 2x minus 2 equal to those numbers with an absolute value of 16, so we're going to have positive and negative 16. So we got the backdrop, and we have in the creation of the equations that will enable us to solve for x. Okay, so we have that 2x minus 2 is equal to negative 16, and that 2x minus 2 is equal to 16. And so for both equations, okay, we'll add 2 to both sides throughout. Okay, so you have for 2x minus 2 equal to negative 16. So if I add 2, and likewise for 2x minus 2 is equal to 16. Okay, so we have at the lower end, we got 2x is equal to negative 16 plus 2, which will be negative 14. And with division by 2, we will have that x is equal to negative 7. For 2x minus 2 equal to 16, adding 2. So we're going to have that 2x is equal to 18. And we have with division by 2, we'll have that x is equal to 9. And so for what we have in the case of our values in x, that will satisfy this particular absolute value equation. Okay, we come out to negative 7 and positive 9. Okay, now I had mentioned that we would be going back to radical equations, and I wanted to hold off until the very end, this particular part. And I think there might be something in the mix from Alex that will have in this other category of radical equations. And this will be in the category of what we have for an equation with two radical terms. And I'll admit that for problems of this type, there can be some situations where it might be quicker to get to the final answer if you were to guess and kind of do the hunting and the pecking, especially if you're looking at testing using a calculator. And what I mean by this, okay, if you have an equation with two radical terms and you're looking at solving for x, and we'll say for this particular equation, when this one have two radical terms, we can say we have the square root of 2x plus 14, and say we have minus, okay, the square root of x plus 3 is equal to 2. So notice we have two separate radical terms in the square root, okay, where we have the square root of 2x plus 14, and we have the negative of the square root of x plus 3. And if I'm looking at solving or setting the stage where I can solve for x, what I'm going to do here is isolate one of these radical terms. And your author would say something like isolate the more complex radical term. Not that one is necessarily more complex than the other, but in this case, this to be interpreted as the first term since it has at least a higher coefficient in x. So if I go at this route, okay, so I can isolate the square root of 2x plus 14 upon adding the square root of x plus 3. So I'm going to have on the left, okay, it's going to be the square root of 2x plus 14, and I have is equal to 2 plus the square root of x plus 3. So I have a radical isolated, and I can free up at least 2x plus 14, even though I'm not going to be able to quite do completely with x plus 3, but I can square both sides. Okay, so if I squared the left-hand side, okay, so I have 2x plus 14. Let's see. Okay, the exponent to that is to get rid of the square root. Yeah, so think like this. Okay, so that all right. Now for what we have on the right, I'm just going to mention. Okay, so just on the side here. You have 2 plus the square root of x plus 3 to the second. Okay, so if I were to take the FOIL, and I'm just going to mention, okay, so you have like 2 times 2, okay, so that's going to be 4. You have the outside term, so you have 2 times the square root of x plus 3. There we go. So you have 2 times the square root of x plus 3. For the inside, you had the square root of x plus 3 multiplied by 2. This is going to be like your inside. Now, for the last product, you had the square root of x plus 3 times itself. I just mentioned, okay, so if you got square root of x plus 3 times itself, okay, so anytime you have repeating term, okay, that's just going to go to x plus 3. Like the square root of 4 times the square root of 4 would go to 4. So we have 2 terms in the last product, okay. And so gathering what we have now, okay, so you got 4 and 3 will be 7. And we have in the square root of x plus 3, so you have 2 square root of x plus 3 plus 2 times the square root of x plus 3. And for, okay, we've already gathered the constant, so we have this x left over. Okay, again, so I have 4 plus 3 is 7. These two middle radical terms have 4 times the square root of x plus 3 when combined. And we've got that plus x left over. So just going back to our equation, okay. So we got 7 plus 4 times the square root of x plus 3 plus x. All right, so notice you still have a radical with the square root of x plus 3. Okay, and if I isolate the radical, okay, so I can take x away and 7 away. And here we have 2x minus x. Okay, so this will be x. 14 minus 7 becomes 7. And for 4 times the square root of x plus 3. Okay, so I have this by itself. Okay, what I can do now, okay, this is a special situation. I can divide by 4, but if you don't care to work with fractions, I know I'm not the biggest fan of fractions, we can go ahead and square both sides. And for x plus 7 raised to the second, okay, so if I square out x plus 7 times itself, okay, so we have x squared plus 14x plus 49. Now for what I have to the right, now there's a bit of a trick to this. 4 squared is going to be at 16, and the square root of x plus 3 squared is going to be x plus 3. Now squaring this expression, okay, you're squaring out the factors, but we still have the multiplication to perform. Okay, there we go. So we got x squared plus 14x plus 49. And distributing 16 over the quantity of x plus 3. So you have 16x plus 48. Now we've got a quadratic equation. Okay, so if I set this equation up in standard form, so I can take away 16x as well as 48. So I'm going to have x squared, 14x minus 16x becomes negative 2x. 49 minus 48 becomes 1. And it looks like we're going to have a squared trinomial. So you have x squared, so you have factoring to x and x. Factors of 1 that will add to negative 2. We have x minus 1 and x minus 1. So we have a repeating factor with x minus 1. So there is one potential solution for this. And that is going to be at x is equal to 1. Okay, so if we scroll back up, so for x equal to 1. Okay, so if I plug in 1 for x, okay, so I'll just write this. So checking x equal to 1. Okay, so if I plug in 1 for x, because I got 2 times 1 plus 14 in the square root, and you have minus the square root of 1 plus 3. So we got 2 times 1 is 2 plus 14, so we're going to have the square root of 16 minus the square root. 1 plus 3 is 4. And we have the square root of 16 is 4. And you got minus. Now the square root of 4 is going to be at 2. And 4 minus 2 is equal to 2. And 2 is equal to 2. And x equals 1 is going to check out. And as I recall, there is an exercise in ALEKS. It does have a bit of an equation, a radical equation that has 2 radical terms. And this is a sample of an equation that has 2 radical terms.